All right, so in this case here, we're going to analyze the graph of the natural log of 1 plus x squared. Now in this case, it's important to remember that square is still within the logarithm, so it's looking like that is really what we intend by this. It's not the logarithm squared, it's the argument of the logarithm being squared. Anyway, let's just jump right in with how we normally attack these things. First of all, we're going to take a look at the domain. Okay, and remember in the domain we're assuming we're going to take the log of something that's positive here. So we're assuming that 1 plus x squared is going to be greater than 0. So the question is, where is that true? Well, when you take a quick look at this here, notice that 1 plus x squared, okay, is always going to be positive because of the square there. So then the question really is there ever a point where it goes to 0? Well, if I take the square root of both sides, I'm going to get 1 plus x greater than or 0, okay. Now, anyway, bring that x, actually, this could have gone one of two ways here. Sorry, when I take the square root, as soon as I did it, I knew that I'd messed that up here. It's either going to be, sorry, if I take the square root here, it's either going to be 1 plus x is greater than 0, or 1 plus x is less than 0, okay, because of the negative that pops out of that. And so either x is greater than -1, or x is less than -1. So essentially what this boils down to here is that x cannot equal -1, and that's your domain. Okay, because if x is equal to -1, -1 plus 1 is 0, squared is 0, and 0 isn't bigger than 0. So there's our issue there, okay? Can't be 0. Now let's take a look at the intercepts. Well, we'll go over here. Okay, intercepts. Now, let's take a look at, well, let's take the low-hanging fruit here. Let's do the y-intercept first. And that's going to be where I let x equal to 0. So that is going to be where y is equal to the natural log of 1 plus 0 squared. Okay, well 1 plus 0 is 1. Squared is going to be 1, and the natural log of 1 is 0. So the y-intercept here is 0. Okay, which implies that we've got the graph going through the origin. So I'm assuming that the x-intercept is going to include a 0 in there as well. When we do this, when we take, okay, when we are looking for the x-intercept, remember we're setting this equal to 0, and that creates an equation that we've got to solve. Now the first thing I'm going to do to solve this equation is realize that it's a logarithmic equation. So I'm going to get rid of the logarithm to start off with. So the base is 0. I'm sorry, the base is e. So e to the 0 is going to equal 1 plus x squared. And e to the 0 is just 1. So 1 plus x squared is equal to 1. Take the square root of both sides, and I'll get plus or minus 1 is 1 plus x. So when I subtract that 1, okay, if I'm using a positive 1 here, positive 1 minus 1 is 0, and I knew that. I mean, I knew that the origin was an issue. And then -1, sorry, minus 1 is going to give you -2. So here are our two x-intercepts here. Okay, x-intercepts are 0 and -2. Awesome. All right, now what else have we got here? Let's look over here. We have got to look for asymptotes. Okay, well the asymptotes typically occur, okay, with a logarithm. If you think about what just a regular old logarithmic graph looks like, it occurs where the argument goes to 0. So where 1 plus x squared is equal to 0. Take the square root of both sides. Okay, so we are going to, whoops, sorry, you couldn't see that. We are going to get a vertical asymptote here, okay, at x equal -1. Which sort of makes sense here because that was the one kind of non-permissible value that I got out of that whole thing there. All right, good. Now let's take a quick look at where the function is either greater than 0 or where the entire function is less than 0. Okay, so we're looking for where the graph is above the x-axis or below the x-axis. Once again, when you're talking about just a straight old, let's go over here, we're talking about just a straight old log function. Okay, the log function is less than 0, okay, when you're taking the log of a fraction. But when you're taking the log of something greater than 0, that's when it becomes greater than 1. Wow. Okay, between 0 and 1, the log is going to be negative, and then when the values of the argument are greater than 1, that's when it's going to be positive. So here, the function is going to be above the x-axis when the argument is greater than 1. So here we go. So we've got 1 plus x squared. I am interested in where this thing is greater than 0. I want the log to be greater than 0, and I've just established that that's going to be where that thing is greater than 1. Okay, as long as the argument of the logarithm is greater than 1, when you take the log, you're going to get a positive value here. So now take the square root, and what we're going to get here is either 1 plus x is greater than 1, or 1 plus x is less than negative 1. Okay? Now hopefully that's something that you are quite familiar with back from Math 20 when you would have first seen that. Bring that 1 over, and this is going to occur where x is greater than 0. And I kind of had a suspicion that that would work here because I knew that the graph crossed the x-axis at 0. So as long as x is greater than 0, that's going to be a positive. Here, if I subtract the 1 from both sides, or negative 2. So as long as the graph is greater than 0 or less than negative 2, the function is going to be positive. It's going to be above the x-axis here. Over here, where is the function going to be below 0? Well, that is going to be where 1 plus x squared is less than 1. Okay, but at the same time greater than 0. Okay, got to be greater than 0 because I don't want to take the log of 0 there. Well, we've already established that this thing goes to 1. This thing is going to go to 0 when x is going to be negative 1. And I already kind of know where it's going to be greater than 1. So I can kind of intuit what's going to happen here. Essentially, this is going to be when x is going to be between negative 1 and 0. However, but x cannot equal negative 1. I've already kind of laid the foundation. I've got all the other bits of information here. I don't even really need to do the algebra on this one. I already know what's going on there. Okay, so there we go. I've got the domain. I've got the asymptote. I've identified the intercepts, and I know where the function is going to be positive and where it's going to be negative. Okay, now let's jump in and let us take the derivative, and we'll investigate intervals of increasing and decreasing. Okay, so our derivative here, I'll write out the function again. Whoops, sorry, our function looks like this. So our derivative, okay, you could do this one of two ways here. Another way that you can do this is to bring the exponent down, but I'm going to take the derivative just like this. I'm going to take the derivative in both these ways here. So here, initially this is going to be 1 over 1 plus x squared, and then we're going to multiply by the derivative of the numerator, which would be 2 times 1 plus x. One of the factors of 1 plus x are going to cancel. I'm going to be left with 2 over 1 plus x. There's my derivative. Or I'm simply going to write 2 for that leading coefficient, and then the derivative of the natural log would be 1 plus x. So either way, I'm getting the exact same value here. So it might be easier to apply the laws of logarithms first before you take the derivative. Okay, now let's talk about critical numbers. Okay, my critical numbers are going to occur. Okay, my critical numbers are going to occur where the first derivative is either 0 or undefined in the domain of the function. Well, this thing is undefined at negative 1, but if I go up here, I've already established that x can't be negative 1. Okay. And because my numerator is 2, well, 2 isn't 0, and I know that's an obvious thing to state, but it's important to recognize that 2 isn't 0, so this thing actually never goes to 0. So it neither goes to 0, nor is there a critical number because it's undefined someplace. So there are no critical numbers. which is basically a way of saying there are no local max or min values here. Okay. However, when I investigate the intervals of increasing and decreasing, bear in mind that there was a spot here where the graph was undefined. There was that vertical asymptote. So if we take a look, if you plug a negative value into this, okay, less than -1, so let's throw in -10. That's going to be -9 in the denominator, so the whole fraction is going to be negative, so it's negative over here. And if you throw a value of x greater than -1, it's going to be positive over here. So indicating that in this interval here, this is going to be decreasing from -infinity to -1. And I'm using parentheses here because this is an asymptote, and I can't include it. Okay, and it's going to be increasing on -1 out to positive infinity. And again, I'm using parentheses here because I'm not including the -1. It's an asymptote. If it had been a maximum or minimum value, if it had been a critical value, I would have included it with square brackets there. So anyway, there we go. No critical numbers, no maxes or mins, but we do have intervals of decreasing and increasing here. Now let's take the second derivative. So this will be 6. Okay, so you know what? I'm kind of a lazy sort of thinker here, so I'm going to rewrite this as 2 times 1 plus x to the -1. I'll take the derivative of that as my second derivative. So that's going to be -2, 1 plus x to the -2, and then I'd multiply by +1 as the derivative of the inside portion here. So that's simply going to be -2 over 1 plus x squared. Okay, well good. Now I am going to start to look here for possible points of inflections or cusps here, and that's going to occur where the second derivative is either 0 or undefined. Now, but again, in the domain of the function. So this thing is undefined at -1. Again, that's not an issue because I don't care. It's not inside the domain of the function, so that's not the issue here. And this thing never goes to 0. Okay, because there's a -2 in the numerator. So I'm not getting any points of inflection. There's no points of inflection here or cusps. Okay? But we can still investigate the intervals of concavity because that asymptote is a natural place where the concavity could change. So, but it's an interesting thing, this second derivative. Notice that no matter what you plug in the denominator, other than -1, because at -1 it's undefined, but any other number that you plug into the denominator that for x there, the denominator is going to be positive because of the square, and so the whole second derivative will always be negative. So it's going to be negative here and negative here. So this thing is concave down on the interval -infinity to -1, union -1 out to infinity. And again, notice I'm using parentheses here because I'm not including the -1. So this thing is always basically concave down. Now, bear in mind that that does not mean that -1 is a cusp. Okay, it would have to exist in the domain of the function to be a cusp. It's a vertical asymptote. So now let's sketch this thing. Okay, so here's my graph. So what have I got this far? I know that it goes through at 0. I know that we've got a vertical asymptote at -1, and I know that we had an x-intercept at -2. So now let's take a quick look at the increasing and decreasing. I know that my increasing and decreasing changes at -1. It's going to be decreasing here, increasing here. And my concavity, if I draw a number line down here, my concavity also only changed at -1, but it didn't change. However, -1 was this natural boundary here. So now think about this. What's going on here? It's decreasing and concave down, goes through here, and it's got a vertical asymptote. Well, the only way that can happen is if it looks like this. Now from here, it's increasing, still concave down, and goes through the origin there. So it's got to look like this. There we go. That's what our graph looks like. Now if you go to your calculator, and I'll show you what I did, because I've already got this on my calculator here. If you if you look at that here, doesn't it look like it's got a minimum value right there? Like that, honestly, that looks like a cusp. The reason why it's looking like that is because the calculator has a very, very hard time drawing that really, really fine line there where those two come together asymptotically. Okay? If you were to zoom in that, you'd see that this actually goes further and further down, but you have to zoom in to see that kind of definition because the screen's just not, just the definition on the calculator screen is not high enough to show that clearly. All right? I hope that makes sense.